My name is John Moises Rigor, and I'll be reporting about multiplexing, frequency division multiplexing, and basic concepts of frequency division multiplexing. What is multiplexing? Multiplexing is the process of combining signals from multiple sources of transmission across a single link. This aims to share a scarce resource. For example, in telecommunications, several telephone calls may be carried using one wire. Multiplexing originated in telegraphy in the 1870s and is now widely applied in communications. In telephony, George Owen Squire is credited with the development of telephone carrier multiplexing in 1910. Path refers to the physical link. Channel is a portion of the path that carries the transmission between a given pair of devices. Frequency division multiplexing, or FDM. Here you can see three devices or three sources. The signals from these devices are being sent to a multiplexer or MUX, then across a communication channel, then towards the multiplexer or DMUX that reverses the process of multiplexing. Frequency division multiplexing is an analog technique that can be applied when the bandwidth of the link is greater than the combined bandwidths of the signals to be transmitted. FDM uses a carrier signal at a discrete frequency for each data stream and then combines many modulated signals. Here are the basic concepts of FDM. The signals generated by each sending device modulate at a different carrier frequency. The modulated signals are combined to a single composite signal that can be transported by the link. Channels are separated by strips of unused bandwidth to prevent signals from overlapping. Carrier frequencies are separated by enough bandwidth to accommodate the modulated signal. The bandwidth ranges are the channels where the various signals travel.
Wave division multiplexing, or also called as wavelength division multiplexing. It is one of the most important and most popular method to increase the capacity of a standard single fiber. Conceptually, the same as FDM or frequency division multiplexing, except that the multiplexing and the demultiplexing device involve light signals transmitted through fiber optic channels. It uses same idea as refraction. Many different colored light are combined by the WDM multiplexer and put into a single standard fiber. Each color is coded channel. And on the receiving side, each color is separated into its own channel by the WDM demultiplexing device. Next is the time division multiplexing, the technique of combining signals from low-speed channels to share time on a high-speed path. TDM is transmitting different users' digital signals over one link by dividing time into slots or intervals and assigning them equally among these users.
Hanggang saan aabot ang 20 pesos mo?
So good afternoon, I am Aiesha Zoe Elevado, and I would be continuing the discussion for the frequency division multiplexing process, or the FDM process. So each telephone generates a signal of similar frequency range. Next, the multiplexer modulates these similar signals to different carrier frequencies. And finally, resulting modulated signals are combined into a single composite signal that is sent over to the media link, plus the extra bandwidth for the guard bands. So the following slides would explain the FDM process in detail. So each physical channel can be characterized by its available bandwidth, and the set of frequencies available for transmission ranges from F minimum to F maximum, as shown in the figure. Next, Such bandwidth can be divided into subchannels, and we can associate a communications to each subchannel, seen in the figure. So the solid bandwidth that was shown on the previous slide is now divided into subchannels. Finally, the signal related to one communication is filtered and then modulated, hence shifted in frequency, in order to fit exactly into one subchannel. And the note above explains the figure. For the demultiplexing, it uses a set of filters to decompose the multiplexed signal into its constituent component signals. Next, the signals are passed to a demodulator that separates them from their carriers and passes them to the waiting receivers. So in this slide, we could see the frequency division multiplexing hierarchy. And in this example, it was given that the frequency would be 4 kHz. So in a group, there are 12 voice channels and there are 48 kHz. For a supergroup, there are 60 voice channels with a frequency of 240 kHz. A master group has 600 voice channels with a frequency of 2.52 MHz. And finally, for a jumbo group, there are 3,600 voice channels with a frequency of 16.984 MHz. So for this slide, it shows the table for the FTM analog hierarchy. It shows the relationship of the level and the number of voice band channels. So for a basic group, there are 12 voice band channels. For a basic supergroup, it has 60 voice band channels, equivalent to 5 groups. For a basic master group, it has 600 voice band channels, equivalent to 10 supergroups. For a jumbo group, it has 3,600 voice band channels, equivalent to 3 master groups. And for a super jumbo group, it has 10,800 voice band channels, equivalent to 3 jumbo groups. And that would be all. Thank you.
Introduction to pulse modulation. Pulse modulation is the process of converting the analog signal into digital pulses. It is also a type of modulation in which pulses are varied in some respect, such as width or amplitude, to represent the amplitude of a signal. There are 4 types of pulse modulation techniques. Number 1 is the pulse width modulation. The pulse width is made proportional to the amplitude of the analog signal. In pulse width modulation or pulse duration modulation, the width of the pulse carrier is varied in accordance with the sample values of message signal, or modulating signal, or modulating voltage. In pulse width modulation, the amplitude is made constant and width of pulse and position of pulse is made proportional to the amplitude of the signal. We can vary the pulse width in 3 ways. Number 1 is by keeping the leading edge constant and vary the pulse width with respect to the leading edge. Number 2 is by keeping the tailing constant. Number 3 is by keeping the center of the pulse constant. We can generate pulse width using different circuitry. In practical, we use this 555 timer, which is the best way for generating the pulse width modulation signal. By configuring the 555 timer as monostable or a stable multivibrator, we can generate the pulse width modulation signal. PWM signal generation has a number of ways. In demodulation, we need PWM detector and its related circuitry for demodulating the PWM signal. One of the advantages of pulse width modulation is that Like pulses position modulation, noise interference is less due to amplitude has been made constant. The second technique is the pulse position modulation. The position of a constant width pulse within a prescribed time slot is varied according to the amplitude of the signal. In the pulse position modulation, the position of each pulse in a signal by taking the reference signal is varied according to the sample value of message or modulating signal instantaneously. In the pulse position modulation, width and amplitude is kept constant. It is the technique that uses pulses of the same breadth and height but is displaced in time from some base position according to the amplitude of the signal at the time of the sampling. The position of the pulse is 1:1, which is proportional to the width of the pulse and also proportional to the instantaneous amplitude of sampled modulating signal. The position of the pulse position modulation is easy when compared to other modulation. It requires pulse width generator and monostable multivibrator. Pulse width generator is used for generating pulse with modulating signal, which will help to trigger the monostable multivibrator. Here, trial edge of the PWM signal is used for triggering the monostable multivibrator. After triggering the monostable multivibrator, PWM signal is converted into pulse position modulation. For demodulation, it requires reference pulse generator, flip-flop, and pulse width modulation demodulator. One of the advantages of pulse position modulation is that low noise interference when compared to PAM because amplitude and width of the pulses are made constant during modulation. The third one is the pulse amplitude modulation. The amplitude of a constant width, constant position pulse is varied according to the amplitude of the analog signal. In pulse amplitude modulation, the amplitude of a regular interval of periodic pulses or electromagnetic pulses is varied in proportion to the sample of modulating signal or message signal. This is an analog type of modulation. In the pulse amplitude modulation, or also known as PAM, the message signal is sampled at regular periodic or time intervals, and each sample is made proportional to the magnitude of the message signal. These sample pulses can be transmitted directly using wired media, or we can use a carrier signal for transmitting through wireless. There are two sampling techniques for transmitting messages using pulse amplitude modulation. One is the flat top PAM or pulse amplitude modulation. The amplitude of pulse is directly proportional to instantaneous modulating signal amplitude at the time of pulse occurrence and then keeps the amplitude of the pulse for the rest of the half cycle. For the natural PAM, or also known as pulse amplitude modulation, the amplitude of each pulse is directly proportional to the instantaneous modulation signal amplitude at the time of pulse occurrence and then follows the amplitude of the modulating signal for the rest of the half cycle. The last technique is the pulse code modulation. The analog signal is sampled and converted to a fixed length, serial binary number of transmission. Pulse code modulation is first introduced by Alec Reeves in the year of 1937. In the pulse code modulation, analog signal is reconstructed to digital signal for ease of transmission by using the analog signal samples. In technical terms, PCM will transmit the analog in a digital form, whose signal is sampled at regular intervals of time and quantized at same quantum levels to digital code. We know that digital code is nothing but binary code which consists of ones and zeros. That is logic 1 and logic 0. So we will transmit the digital data in the form of ones and zeros. When the signal is received by the receiver, the modulator in the receiver will demodulate the binary signal back into the pulses with the same quantum levels, like in modulator, and these pulses are again used for generating or regenerating the required analog signal. So one of the advantages of pulse code modulation is that pulse code modulation will have noise, addition, and data loss is also very low.
Application of multiplexers. There are many applications for time multiplexing. In computer science, they include sharing access to a commonly used resource among several consumers. A couple of significant examples include communication system. A multiplexer is used in communication systems which has a transmission system and also a communication system. So multiplexer is used to increase the efficiency of the communication system by allowing the transmission of data such as audio and video data from different channels via cables and single line. Next one is computer memory. Computer memory, a multiplexer is used in computer memory to keep up a vast amount of memory in the computers. And also to decrease the number of copper lines necessary to connect the memory of other parts of the computer. Next is process execution. This is what we call context switching. It shares processor execution time among the tasks that need to be executed by the computer. By processing each time slot quickly, then switching between them, a computer can give the impression that it is executing multiple activities at the same time. Lastly is the telephone network. Telephone network. A multiplexer is used in telephone network to integrate the multiple audio signals on a single line of transmission. That's all. Thank you.